All right, in this tutorial we're going to create a hierarchical schematic in Xschem and run a couple of simulations on it. So the first thing we're going to do is launch Xschem, and we're going to make it full screen here. Now we're going to start out by making a schematic, and in our basic schematic is going to be that of an inverter. It's going to look a little different than the inverter that we made in the last tutorial. We're going to use 4-terminal NMOS and a 4-terminal PMOS for this particular inverter. Oops, and that's what happens if you don't deselect the thing that you had previously selected. It gets picked up and moved around as you instance the new symbol. So now let's wire up the gates here. Wire up the drains. And what we're going to do is wire the body connection of the MOSFET up to the source, and maybe give it a little more of a stub there. And now we're going to attach some pins to these 4 terminals. And the reason I'm using a 4-terminal MOSFET here and not the 3-terminal MOSFET is so that I can explicitly propagate the power supply connection into the cell via pins. It's okay to use the default bulk and bulk connections in the 3-terminal symbols. The problem with that could potentially arise is that if you forget to connect power up, especially in the layout, that can create a real problem, because if you use global net labels in Magic to connect things up, and then at the last stage when you do your layout you happen to forget to connect the well up someplace with an actual metal connection, you'll have a floating well and your chip may not work because of that. Very likely will exhibit strange behavior that you did not intend at the very least. And so it's probably not a bad habit to actually propagate explicitly the power supply connections into the schematic, at least for the schematics that you're using to do layout versus schematic verification. So I'm just going to do that in this particular case. Sometimes you'll see me propagate the power supplies into a subcell explicitly, but use 3-terminal MOSFET connections because I don't want to have the 4th terminal running around because of the way I make my schematics. And so you just have to be careful. But in this particular tutorial, we're going to explicitly put in the power supply connections as terminals in the symbol that we create. So we're going to need to get some pins, and those again are symbols in the Xschem device library. And so for the input, we're going to use an I pin connected here. And we'll change this to, we'll call the input to the inverter A. And these pin labels have to match the symbol port labels. So let's get an I/O pin for the power supply connections. And so we'll go Alt-R to rotate this. And again, I forgot to deselect this one, so I'll have to fix that. And let's change this to, I don't know, VP for the positive power supply. And let's copy this, the C key, and then Alt-R a couple of times, and we'll call this the negative power supply pin, VN. And let's create an output label, or an output pin label, which is O pin. let's call this Y. Okay, so there's my inverter schematic. So we're going to save this as, let's see, put this in Documents, Inverter Tutorial. I'm going to call this inverter.schem, or SCH, inverter. Okay. Okay, so now we're going to create a symbol to go along with this schematic. So we're going to go New Symbol. And now the first thing we're going to do is create some symbol pins. And going to configure this. So this is going to be A, and the direction is in. So I right-clicked on that to configure it, and we're going to place another one, and we're going to call this one, actually I guess I should probably do it in the same order that I created them. Well, actually I guess it probably doesn't matter that much. So we're going to call this one Y, and this is going to be an output pin. This will be, I'm right-clicking on those to configure them. This will be VP for the positive power supply, and this is an in-out. And then I'll copy that by hitting the C key, and this will be our negative supply pin. This will be an in-out as well. Okay, so I'm going to zoom in here. And now, right now I'd like to be able to draw my symbol, which is going to be, you know, like a triangle with a little circle here. And in order to do this, I want to change the grid. So the current snapping grid is 10 units, 10 pixels, and the display grid is 20. And probably I'm going to need to make the grid down to maybe 2.5 to really get a nice looking symbol here. So you can do that by hitting the G key. So the G key cuts the grid size in half, and you can see that the green background turned red to indicate that this is not a safe grid spacing for creating the port labels. You want the symbol port labels to be on the 10 unit grid, really. So if you hit Shift G, that goes up by a factor of 2, G goes down by a factor of 2. So I'm going to go down to, let's say I start out at 10, and now I'm going to hit L to make a line, and then you click to complete the line. So there's a triangle. I don't particularly like where that is. I'm going to go down by a factor of 2 to 5, and I'm going to select this and then hit the M key to move. And I kind of like where that is. And now I'm going to create the lines that bring this down to here, this up to here, this over to there, and then that's going to be my bubble on the output of the inverter. Now, to draw the circle is a little strange. So if you go up here to, let's see, symbol, let's see, tools, it's tools. So insert circle, you'll see it's Shift Control C. And the way it works, I'm not sure that you can actually use the menu option to initiate this. I think you actually have to start with the cursor over the first position. And so I'm going to hit Control-Shift-C, and you can see now I have a little rubber banding line here, and that lets you put a second point on the circle, which I'm going to put over here at the opposite of the diameter. And then the third point is a point that's going to be on the circle. And so it takes a little bit of while to get used to how to draw a circle with this thing. But there's my circle. And not sure I like that. I think I might want to make the move this over, and maybe I'll delete that and then make another line. Oop. To extend that out a little bit. Yeah, that looks reasonable. Okay, so that's the symbol. I do need to configure the global properties of the symbol. So if you hit, I think it's the Q key with nothing selected, you have this text box that comes up to configure the global properties of the symbol. And so we need to make the type equals subcircuit, and then we're going to make the format and then you go and name and pin list and or at sim name, and then template equals name equals, we'll call this x1. X is the SPICE reference designator prefix for subcircuits, and the 1 is sort of the default number, but if there's another x1 someplace in the schematic, it will automatically generate a unique number for that. And I think that's all we need to do for this. And now we can save this as, and we're going to put this in our, let's see, it's in Documents, Inverter Tutorial, and we're going to call this inverter.sim. Okay. All right, so now we have a symbol and an underlying schematic. Now we're going to take this one level further, and we're going to actually create a second level of hierarchy. So we're going to create a new symbol, or rather a new schematic, and this is going to be a double inverter buffer. Now this is really overkill, but I just want to show you a sort of a two-layer hierarchical schematic. So we're going to instance or insert a symbol, and we're going to insert a symbol from our inverter tutorial library, which is our inverter sim. So there's our inverter symbol, and we're going to copy, actually, you know what? I want to change my inverter symbol. Okay, I wanted to add one thing. Open, no. I wanted to add to this inverter symbol a text property here, which is at name. And we're going to make this 0.2, and I'm going to move this up, and I want to change the grid to 5 so I can move it over a little bit, get it closer in there, and now I'm going to save it. Okay, now we'll make our new schematic. New schematic. Insert symbol. Shift I. And so now you'll see that this is X1. And if I copy this here, there's X2. Okay, so now I've got my two inverter symbols, and now I'm going to connect them up. Output of one goes into the input of the next one. I'm going to connect the power pins together. Put a little stub over here for the input and the output. All right, so that is our higher level schematic. And we're going to need to add some pins to this. So insert symbol and the same kind of thing. So we're going to go into the devices library and grab an I pin for the input. Again, we'll call this A. I'm going to insert Shift I IO pin for Alt R to rotate it a couple of times. And we'll call this again VP for the positive power supply. I'm avoiding using the name VDD and ground just because those are global names, and so it'd be better to not have those names also in the port list of a sub-circuit definition. Change that to VN, and now we want an O pin. Not sure if I unclick that or not, so let's just blow that one away and instance a new one. Let's call this again, let's call it Y, because why not? All right, there's our buffer. Schematic, and let's save this as buffer .sch. Don't forget the dot. Okay, now we have to create a symbol for the buffer. And again, we can put down some symbol pins. And we will right-click on this. This will be our input pin. A. Our output pin Y. Power pin VP. This is an in-out. Let's copy this one. VN. And now let's, I guess, draw some lines. Let's turn the grid down to 5. Move this over. Turn lines for the okay, there's our awesome buffer symbol. And again, let's put a text in here to show the instance name. Insert text, and we'll call this @name. Move this up. Okay, and we have to configure global properties, so hit the Q key, nothing selected. This is going to be type subcircuit, format, and again it's going to be and name and pin list, or rather @pin list and @sim name, and then the template is going to be name equals x1. Save this as buffer .sim. Okay, so let's make our new top level schematic, which is going to have our sort of simulation paraphernalia in it as well. So we're going to insert a symbol, which is our buffer. Okay, that's x1. And let's grab our TT models and such. So under libs, madvlsi, TT models. Put that over there. Let's get a VDD symbol and a ground symbol. Let's move this up a little bit there, and let's get a couple of voltage sources. This will be VDD 1.8. And connect that up to VDD and ground. So let's copy this to make our input source. Call this V in. And let's make this our pulse. Call pulse parentheses 0. 1.8, 1 nanosecond, 1 nanosecond, 1 nanosecond, 4 nanoseconds, 10 nanoseconds. Just like we had before. Let's move that over a little bit. All right. And let's connect the input and the output up through pin labels. So that's under libs and devices, lab underscore pin. And this will be the in. I can copy that and rotate it a couple of times. Connect that up. Copy this over here. Call this V out. Okay, we're almost there. I need to put in the spice, the code shown. And we'll call this spice. And the value will be .tran 0.01 nanoseconds and 1 microsecond, and then .save all. How about that? All right, so let's save this. As, call this buffer tran schematic. All right, so a couple things here. One is if everything is hunky-dory, I can select that and I can hit the E key and descend into the child schematic. If I hit, I think it's Control E, that'll go back up. So you can descend and ascend in the hierarchy with the E key. So select the symbol, descend in. If I want to descend into X1, I can select that and descend in down to the transistor level. And if I go Control E, I'm back up to my top level schematic. So that's kind of super cool. Let me unhighlight all. Yes. I'm gonna move this a little bit so it's more centered. And let's just take a look at the net list. What we get. All right, so you can see here our net list consists of the buffer symbol, V in, V out, VDD, and ground, and the 2 voltage sources. And then this is from the code that's inserted by the TT models, the code that's inserted by the SPICE code block here. And then down here we have the subcircuit definition that expands out the buffer symbol. And these in turn are subcircuits, which are expanded out here in this, which is where our transistors actually are. And then we've got the global VDD and ground. So that looks plausible. And so let's try simulating this. Does take a while. Okay, dismiss, and let's see what we can see here. So there's the waveform viewer. I select this pane and make this bigger, and we can take a look at V of V in and V of V out. And let's zoom in here. And yay, verily, we can see the input waveform just like we had in our previous inverter simulation. And then we can see the output waveform, which is in the same sense as the input waveform, but delayed by a little bit. And it has sharper transitions here because of the double inverter that it's gone through. Now we can also look at one of the intermediate nodes inside the subcircuit. So you'll notice X1 is the instance name for our buffer, if you recall that. And there's this funny V of X1.net1. Okay, so if we had labeled that intermediate node between the two inverters with a net label in our second level schematic down one level, this would have been X1 dot whatever that net label was. But because we didn't label it, and there was only one unlabeled net, Xschem called it net1 for us, and so the composite net name is kind of like a path name in a file system. It's going to be x1.net1. So if I click on that, that should be the output of our first inverter inside our buffer. And you can see, yes, that does in fact look pretty much like what we saw in our inverter simulation for the output node. It might be slightly delayed from what we saw just because there's an extra load on the output, which is the second inverter stage. And so that is all very good. If we select this pane down here, we can take a look at I of VDD, and you'll notice again here that the current is very low when the outputs are not changing, but it spikes up to a much higher level when the outputs are changing. So it's about 1.6 nanoamps in this range here. But if we go to one of these spikes where the transitions are happening, it's up in the here 62 microamp range. So that's creating and simulating a hierarchical schematic, and that's it for now. So thanks for watching.